in our last part 3, if you will, of lesson 1.2, we have 3 topics to talk about. Our first topic is going to be even and odd functions and symmetry. So understanding what it means for a function to be even as opposed to a function to be odd. And I'm not sure, I don't think this is a topic we talked about in Algebra 2. So I don't feel like it's, anything that I should be like, oh yeah, you remember this. So functions that are considered even, okay? And there are some values to knowing if a function is even or odd. But if a function is considered even, one way to tell is it has symmetry across the y-axis. Okay, so an even function has symmetry across the y-axis. That means if you graph the equation, you can tell if the function is even or not, correct? Now, do we always have the graph option? Not necessarily. I mean, yes, you have the graphing calculators, but we don't necessarily, there's times where we need to be able to figure it out if it's even without looking at a graph. And so the algebraic option, a function is even if f of negative x equals f of x. So meaning if you go through and replace x with negative x in the function, and your function is still the same, then it's going to be considered even. Okay, so those are your even options. Got it? Now, a function could be even. A function could be odd. If a function is odd, it has what we call origin symmetry. And if we're talking origin symmetry, it's kind of a diagonal symmetry because it's kind of diagonal through the origin. We'll look at some examples and I'll try and explain it when we get to some examples. But with origin symmetry, I also relate it to doing 2 reflections. So like reflecting across the y-axis and then taking that piece and reflecting across the x-axis. So something that has origin symmetry would end up from the first quadrant reflected down into the diagonal 3rd quadrant. Okay, so that's origin symmetry. Again, it'll make a little more sense once I show you on a graph. Algebraically, if a function is odd, f of negative x equals negative f of x. So f of negative x is when you put the negative x in place of x. Negative f of x is just when you take the original function and multiply it all by a negative. Again, I'm going to demonstrate this, okay? But those are the pieces of information you need to know. Now, does this mean all functions are even or odd? No. Functions can be even, odd, or neither. Not every function is going to be symmetric either across the y-axis or the origin. Okay, and so our directions ask us to tell whether the functions are even, odd, or neither and determine their symmetry, which kind of goes along with it. I'm going to look at this algebraically first, because algebraically is the part that is, I think, important, but sometimes a little bit harder for students to know what to do there. And then we'll follow up with the graph. That way I can show you both. So if we are algebraically looking for if a function is even or odd, they give us f of x, right? Start by finding f of negative x, right? Because the first one is if f of x and f of negative x are the same, we know it's even. So start by finding f of negative x first. F of negative x says every place I see an x, I'm going to replace it with negative x. So instead of doing x to the second, what are we replacing that x with? So we're doing negative x to the second. Tell me, what is negative x to the second? What's negative x times negative x? Negative times a negative makes it a positive. And x times x is x to the second. So negative x raised to the power of 2 is x to the second. And we still have the minus 3 there, don't we? What do you notice? Did it stay the same? Yeah. x squared minus 3 ended up equaling x squared minus 3. So algebraically, I don't have to go any farther because I just figured out that f of x equals f of negative x. Since they are equal, what do I know? This function is what? Even. Now, you can pretend you did not do that. And if you didn't do that, what's your other option? You could have gone straight to your calculator, right? Actually, do I even need to graph this one on the calculator? No. What does x squared minus 3 look like?
It's parabola, move to the left 3.
No.
Or is it
Move down 3.
Move down.
Move down 3. Okay, so if you graph this, and I'll just sketch the graph. So if you graph this on the calculator, you get a parabola, move down 3. Well, parabolas in themselves are already symmetric, yes? And if it's on the y-axis still, and it just moved down 3, is it symmetric across the y-axis? Yeah, it is symmetric across the y-axis. So does that support our belief that this function is even? It does. Officially, what was the other question we were supposed to answer? Even, odd, or neither, and determine the symmetry. What kind of symmetry do we have here?
Symmetry. I realized it was stupid when I said it.
Symmetry where?
Across the y-axis.
Across the y-axis. So I'm going to say symmetric across the y-axis. Okay. So there's an even example for you. The algebra did it for us. Technically, depending on the situation, did you even have to do the algebra? Could you have just graphed it or thought about the graph? You could have. Nothing says, and as I said, it depends on the situation, which is why I'm teaching you both sides of this. Nothing says you had to do the algebra here. Yes, looking at that graph tells me it's even. I understand that. But there's important reasons to see both sides of it. Okay?
So on the homework, we'll have this graph and we'll solve algebraic.
I think on the homework, the directions are like this. Tell, is it even, odd, or neither? This doesn't tell me what method to use, does it? And I don't think it says algebraically or graphically. I think you get to choose. So I'd be familiar with both is what I would say. Okay. Next part. G of x equals x squared minus 2x minus 2. Because I want you familiar with the algebra, we're going to start with the algebra. Because the graph makes it easier, doesn't it? Once you understand what origin symmetry means, and we'll get to that. So we're going to start with the algebra. So g of x is given. I always start by finding f of negative x. Or in this case, g of negative x, because I need that for both, right? So I always go there first. So g of negative x says, every place I see an x, it's negative x. So I'm going to do negative x to the second minus 2 times negative x minus 2. Does that make sense? Now, clean it up. What is negative x raised to the power of 2? So negative x times itself is x squared. Negative 2 minus 2 times the negative x is going to make it plus 2x, and then minus 2. What just happened?
2x switch signs.
What'd you say?
2x switch signs.
Okay, 2x switch signs. So at this point, does g of x equal g of negative x? No, those two are not equal to each other. Those are the two we have. They are not equal. So at this point in my problem, I know that this function is what? I don't know it's odd. I know it's not even. Does that make sense? I'm just kind of taking you through the process that, okay, I have ruled this out. I know it's not even. I don't know it's odd because remember there's that neither option, yes? It's not like numbers where the numbers are either even or odd. There is a neither option here. Okay, so plan A failed. Plan B. Now we're going to check if it's odd. We already have f of negative x, right? Or in other words, g of negative x. Now we need to find negative f of x, or in this case, negative g of x. Now, the negative out front says that we take the whole equation and multiply by a negative. So that means I'm going to write it out. I'm going to take negative, and I'm going to multiply it by x squared minus 2x minus 2. So that's me showing my step, so to speak. If you went ahead and went to the answer, that's fine. But it's a negative of the whole thing. And notice I went back and grabbed the original function, yes? Not grabbing our already altered one. If I change this, it now becomes negative x squared plus 2x plus 2. What does that match? Does it match x squared plus 2x minus 2? No, and that is what we were really checking, wasn't it? We were trying to find out, does g of negative x equal negative g of x? And does it equal? No, so what do I know now? This is not odd. So if it's not even and it's not odd, it is neither.
So what would odd look like on the graph?
We'll get there. We still have one more example, right?
That's the next one, Kylie.
I mean, come on.
No, I already.
You know how I teach.
Yeah.
I mean, occasionally, you know. Now, real quick, I want to graph this one just so you can see. It was what? X squared minus 2x minus 2. And you're not going to see it because you're still looking at the absolute value blood bank. Now, the shape itself is a parabola, yes?
Yes.
Parabolas itself are symmetric, right? However, is this located so it's symmetric across the y? No, it's off center. I can't fold that graph on the y and lay it across itself. Symmetric across the origin means you would have to have some matching quadrants, essentially. Like first quadrant would be like a reflection of third quadrant type thing. And I'll explain better when we get there. Okay? But there would be some diagonal quadrants matching up. You're looking at the next graph, aren't you? Trying to understand my explanation there. Okay. Now, mathematically, I want you to see what happens here, right? So forget the graph for a moment. Let's talk algebra. We get to talk h of x this time. First thing I'm going to find algebraically, if I want to know even or odd, is h of negative x, yes? And h of negative x. Is that x to the third on top? It is, isn't it? So we're going to do the negative of x raised to the third over 4 minus negative x raised to the second. Okay, negative x raised to the third. What's a negative raised to the third?
Negative.
A negative. So this is going to be negative x to the third. Now, do not tell me this is minus a negative is a plus. You have to do the negative x squared first. What is negative x raised to the second? Positive. So this is going to maintain 4 minus x squared. Because the minus is still there. It's 4 minus. That negative x raised to the second becomes just a regular x to the second. Okay, does this match h of x? No. As expected, these guys are not equal. So of course, at this exact moment, you're going to tell me I know it's not even. Not that you have, and it's not that you have to write that down. I'm just trying to explain the connections we can make. Now, this is why this is a good one to go through algebraically. Negative h of x. So that means I take the function and I multiply it by a negative. So I'm multiplying the fraction x cubed over 4 minus x squared by a negative. So when I'm multiplying by a negative, that's like multiplying by the number -1, if you will. What is -1 as a fraction? -1 over 1? Or +1 over -1? Here's the deal. When I'm multiplying by a fraction by a negative value, am I multiplying top and bottom by a negative? If I multiply top and bottom by a negative divided by a negative is a positive. And so I'm only multiplying one piece by a negative. You get to choose. Do you want to multiply the numerator by the negative or the denominator by the negative? And what makes sense in this case? If I'm trying to get this to match one of my other equations, if I put that negative up top, it's going to match, isn't it? Or the other option is to just put the negative out front like I have it. But if we write this as the negative of x cubed over 4 minus x squared, what did we just make happen? We made those look equal, yes? And so since they're equal, I now know that it is odd. I haven't graphed it yet. Some of you have, I know. But how do I answer the question about symmetry? What kind of symmetry are we going to see? Yeah, this is going to be symmetric across the origin. Now, let me pull up the graph. Nothing else, so I can remember exactly what it looks like as I talk about it. Remember to do a fraction bar, or put that whole denominator in parentheses. Okay. So, this lovely example is an example of symmetric across the origin. And, I don't know, do I dare try and sketch a little graph here? So, kind of think, would it work? I don't know. When I'm trying to figure out symmetric across the origin, I always kind of think quadrant by quadrant. So like if I look at quadrant 1, and I take it and I reflect it twice, so I have to reflect it across the x and across the y. Doesn't matter which order. So if I reflect this across the x, quadrant 1 is going to then be upside down, yes? But then if I reflect to that piece across the y, what's it do? It lands on top right down here, doesn't it? Okay. If I take, say, quadrant 2 up here, and this curve isn't drawn exactly right, but if I reflect it, say, across the y, then it's a curve up in quadrant 1, but then when I reflect it across the x, it lands on top of itself. Am I making a little bit of sense here? Okay. And it's not that we're reflecting across a diagonal line, because that wouldn't work exactly right, but I think of it as two reflections. But that is an example of symmetric across the origin. Okay. I have a feeling that's a good stopping point. Because I could start talking about asymptotes all I want. However, I'm not going to get very far, am I? Yeah. So, we'll stop here. The homework that goes along with this lesson is 48 through 66 evens. It will not be due till Friday. Okay? You could go ahead and work on the even and odd section of homework if you want to get that done. And that probably starts at 48 because they usually go in order. So there's probably a few lessons you can go ahead and do, or a few questions.